Okay, great. Right. So I was asked to talk a little bit about coastal trapped waves today. So the first thing is, what is a coastal trapped wave? These are a set of waves confined over the continental shelf and slope, and they're strongly affected by Earth's rotation. Consequently, they only propagate one way along shore, which would be away from the equator on the eastern side of the Pacific and towards the equator on the western side of the Pacific. They're really handy for studying wind-driven processes over the continental shelf and slope. Typically, they do a great job hindcasting alongshore currents and pressure. They've been observed frequently in observations, and they work out pretty nicely. What you do is you have a basic theory where the basic version of the theory doesn't include any bottom friction, doesn't include any mean flow. It assumes that the Earth is flat, which is what this mysterious thing means. And it works best for timescales longer than, say, 4 days and less than about 50 days, something like that. And the wave properties depend on things like topography, latitude, and density stratification. Here's an example from a nice paper by Illich et al., where they looked at the modal structures from two different locations off the coast of Peru, 16 degrees south, active margin, and a passive margin off southwestern Africa. Over here is stratification, and then each of these sections are distance offshore and water depth. Ignore the contours and just look at the colors. The red is a large positive value. There's a node through here, 0, and then negative. So with no dissipation, these things are all plus or minus. The lowest mode, it goes at about 3 meters a second, which is about 300 kilometers a day along shore in this example. Higher modes have more complicated structures and propagate more slowly along shore. Let's see, what else? The structure depends quite a bit on the details of the topography and stratification, but two things to notice. One is that the largest amplitudes are almost invariably over the shelf and upper slope. And likewise, especially with the narrow margins, the nodes tend to be concentrated in the upper half of the water column. Okay, so that's what I just said. Here's an example from a paper by Dave Chapman back in the 1980s, where he used coastal trapped wave theory, which gives you a nice, simple first-order wave equation to solve. So all he used was observed alongshore winds, and way off in the distance, he used a coastal sea level record to provide a boundary condition. These are mid-shelf bottom pressure in meters or centimeters of water off Northern California. The light lines are the observations. The heavy lines are the model calculations. So very simple model. And he used, I believe, 3 modes in the first 3 modes in calculating this. So you don't need a lot of modes to get a decent solution. And this is fairly typical of the kind of results people get using this model, which for a simple analytical model is, in my mind, a very amazing result. Now, of course, you're going to do much better if you use a really good regional model like Alex Kuropov is going to be telling us about soon. In terms of using bottom pressure to look at, well, first of all, coastal trapped wave theory will give you will account for a fair bit of your variance over the shelf. Again, I expect you do better with a good numerical model. But in principle, you can, since the modes are mathematically orthogonal, in principle, if you had an intense array of bottom pressure gauges across the shelf and slope, you could take advantage of the orthogonality which involves bottom pressure and bottom slope, and you integrate across the shelf. But that would take a lot of pressure gauges, and it'd be more practical if you wanted to use pressure gauges to find these modes, to just place them in a sensible way in terms of nodes and maxima, and use the least squares approach. The theory, of course, gets more complicated as you do more, as you become more realistic. I include this as an example of what happens when you include bottom friction. With weaker than realistic bottom friction, you basically get everything is either zero phase or 180, with the phase contours here passing through the area with the lowest amplitude. If you include a realistic friction for this example, then these phase contours get smeared out. And if you go to lower frequencies or stronger bottom friction, the structure really gets lost. And as the simple theory can account for modest amount of bottom friction, but it really begins to break down as you go to very low frequencies. Bottom friction, if you include the fact that the Earth is spherical, you lose the orthogonality properties and it becomes messier. But the basic physics is still there, that you have these waves that propagate rapidly along the coast and have high amplitudes over the shelf and slope. So where are we at? These waves have been detected frequently in nature. Some downright beautiful examples have been published. The theory really is central to our understanding of how winds drive currents and sea level changes over the continental shelf. And people have, over the years, dealt with these various complications like mean flow, frictions, and so forth over the years. In terms of where this field is, it was a very active line of research in the 1970s and through the 1980s. And then basically, people started to lose interest in it. And I think from a theoretical standpoint, that loss of interest was largely because a lot of the good problems had been solved, and it was getting to the point where improvements meant going after nonlinearities and using numerical models and so forth.
1 minute.
Okay, thanks. Yeah, so I guess all I should really add is that I think these waves are really exciting, but in terms of using these things to remove variance, for example, from the Alaskan example we saw before, a really well-resolved regional model that really resolves the topography well and does a good job with weather band wind forcing would be just as useful, I think. So that's it.